We're Team 5, and our project is the large-scale implementation of a machine learning algorithm. Our team members are Nicholas Ford, Paul Lathong-Paisan, and Yauman Ahadi. When we say paper or papers throughout this video, we mean paper metadata such as title, authors, abstract, and etc. Our client, Mr. Gonzalez, is a PhD student at UCL and the Alan Turing Institute. He's working on biomedical natural language processing, or NLP. His main research focus is the extraction of pharmacokinetic information using NLP and machine learning approaches. His current machine learning classification algorithm requires a Spark data frame which contains pharmacokinetic papers from PubMed in order to classify this as relevant or irrelevant to acquire a bank of very specific and useful PK/PD papers. The results do need to be tagged with certain information which is useful for searching through these papers for specific studies or specific drugs. The main use of this is for academic researchers and companies to research into pharmacokinetics and develop an understanding about certain drugs and their effects on the body and other related information. Our client's product name will be PKPDAI and will make the relevant subset of papers available on their website for open access use.
Our project consists of building a pipeline that automates the process of downloading papers, classifying them as relevant or irrelevant using our client's machine learning algorithm, and then making the relevant subset of papers available via an API. Our pipeline will act as the backbone of our client's website, which will make the relevant subset of papers available for open access use. Our pipeline will make it easier to find relevant pharmacokinetic information on a single drug, including dosage information, parameters, and demographic information. The original pipeline used by our client only worked on a computer locally, was inefficient, and not automated to process new incoming literature. We have completely redesigned the pipeline to automate it on the Azure cloud service. To exploit the potential of our client's machine learning algorithm, our pipeline must satisfy the requirements of robustness, scalability, optimization, modularization, and that it can be used in production, so that end users can truly benefit from the pipeline's output. The solution should have the ability to update every so often in order to keep the database updated with new and modified papers. Our client has also given us an optional requirement, which is the assistance with development of their website. Given that we have enough time and finish the backend pipeline process, we will then assist our client with the development of their website. For this project, we have developed a microservices architecture using Docker. This architecture features 2 Docker containers, one responsible for the pipeline processes, which are downloading, parsing, classifying, and tagging papers, and one Docker image for the server with API access. This structure will run on Microsoft Azure managed by Kubernetes. A container instance of the pipeline image will run once to set up the pipeline. Another container instance of our pipeline image runs periodically to update the pipeline with new and modified papers. These containers write to and update a data frame volume which stores the classified subset of PK papers. Our server Docker container will then make these papers available via our API. The main technologies we've used are Docker, which we use for container instances of our images, which is responsible for running different parts of the pipeline. We are using Python as our main programming language. We are using a PubMed parser Python library to parse XML metadata of PubMed papers into a Spark data frame, which is then used as an input into our client's machine learning classifier. We are also using bash scripts to efficiently download XML paper metadata from PubMed. We are using PySpark for distributed machine learning tasks. We are using Burn Korea Pub Annotation API to retrieve tagging information for papers. We are also using Microsoft Azure for hosting services for our containers and server. And finally, Kubernetes to manage the pipeline's container on Azure. This diagram shows what we have currently completed and what is yet to be done in the project. More specifically, we have done the following. The initial download of all the PK papers from PubMed, parsing these papers, making a Spark data frame of these papers, successfully connecting our program to the machine learning classifier to classify the papers, and devised a microservices architecture to enable the entire process to run in containers on Azure managed by Kubernetes.
This is our setup script for the pipeline, which runs once when the pipeline is initially being set up. Firstly, this script downloads all papers from PubMed matching the search queries pharmacokinetic or pharmacokinetics. These downloads are run concurrently, 10 at a time, which greatly decreases the overall download time. By using a job log, we ensure that failed downloads are retried until they succeed, increasing robustness. Once the downloads finish, a Python program is run which classifies papers as relevant or irrelevant. First, the environment is set up, defining various variables and configurations. Then, we pass the XML data which we downloaded to a Spark data frame. We pass 5 files at a time, meaning 50,000 papers, since each file contains 10,000 papers. This is done to avoid running out of RAM memory. The parse XML to data frame function is called, which uses a library called PubMed Parser to turn our XML data into a data frame, and then performs some data frame cleaning. This Spark data frame is then passed to the pkfilter data frame function, which uses our client's machine learning classifier to classify the papers provided as relevant or irrelevant. The return data frame is then added to the final data frame, which will contain the relevant subset of papers at the end. Finally, the data frame is customized a bit further before being written to our volume in the form of Parquet files. The update pipeline script downloads papers which are new or have been changed on the PubMed database since the last pipeline update. This script will run periodically, for example once daily or weekly, to update our bank of classified relevant pharmacokinetic papers. This process is very similar to the pipeline setup with a bit of additional logic, so there is no need to explain it again. Our setup pipeline takes just under 2 hours to run. The download of XML papers takes about 10 to 15 minutes, and the parsing and classifying takes about 1.5 hours to run. Thus, for demonstration purposes, we will show the entire download process sped up, and then parse and classify only 10,000 out of the total approximate 500,000 papers.
Our goals for the future are to implement the device architecture or consider other, more efficient designs, test the system on Azure and ensure that it works as expected, implement a server with API access to our database to allow retrieval of data from our data frame of classified and tagged papers, implement Kubernetes to manage our pipeline. Given that we have enough time, we will also participate in the development of the PKPD AI website. Thank you very much for listening.